everyone. Okay, so now we're going to be talking about points in a unit cell and how we can calculate distances, say, between atoms in a unit cell. So this is also something that's covered in the lecture notes, or the course notes that Lasse has handed out. So he describes that you can describe points in a unit cell using this vector R. And this is the equation, so xa plus yb plus zc. So what do we mean by that? So actually a, b, and c, these are just your unit cell base vectors, your unit cell parameters, you know, a, b, and c, those three lengths. And x, y, z are the fractional coordinates of the atoms in a unit cell. So say you have a unit cell. This is just one that I'm familiar with. So this is one, it's an orthorhombic unit cell where A, B, and C have different values, but all of the angles are 90 degrees. And this is just, yeah, how the atoms are arranged in that unit cell. Okay, so let's say we want to just get the distance between these two atoms, the distance between the bismuth atom and this particular oxygen atom in the crystal structure. So this is how we would do it. So we would use this equation, first of all, to get the points between the origin and these two atoms. And from that, we can get the vector between this bismuth and oxygen atom. So let's say we have already the fractional coordinates of that bismuth atom and that particular oxygen. Sorry, there's a typo here. It's O3, so this should say O3 instead of O1. But say, yeah, this is the fractional coordinates of that atom there. I think the coordinates themselves are right. So say for B1, it's a quarter of the unit cell, 0.25 along the unit cell length A or X. It's 0.26 along Y down the page and 0.25 up the page. And yeah, those are the coordinates for that oxygen atom. Okay, so R, let's get this vector R for our bismuth. So we go from the origin to that position in the unit cell. So that vector from the origin to that point in space, to that atom, we can use this equation. So X is that unit cell, or excuse me, that fractional coordinates along X. A, so this base vector, we put this in matrix form. So it's say like 8.54 angstrom along the yeah, X direction in real space, let's say. But the A axis, it doesn't go along Y or Z. So those values in the matrix are 0. So it's 8.54 angstrom along X. So then for this part here, YB, so again, for Y, we put in that fractional coordinate here, 0.26. And then for B, our base vectors, so we're going 0 angstrom along X, 4.67 angstrom along the Y direction. So that's our unit cell parameter B, and then kind of 0 angstrom along C. And then for the final part, we have our final fractional coordinate 0.25, the value for Z here, times this matrix. So again, 23.71 angstrom along the Z direction. So if you sum this up, so 0.25 times 8.54 gives you 2.14. So actually, if we were to multiply out this, you would get 2.1400, because 0.25 times 0 is, of course, 0, and 0.25 times 0 again is 0. If you take 0.26 times 4.67, then you get 1.21. So then you end up with a matrix that's 0, 1.210. And finally, 0.25 times 23.71 is 5.93. So 0, 0, 5.93 And if you add those three up, then you end up with this one vector going from the origin to that bismuth position. So these are in units of angstrom now, not fractional coordinates. So you go 2.14 angstrom along the x direction, 1.21 angstrom along the y direction, and 5.93 angstrom along the z direction. So that's our vector from the origin to our bismuth cation. We can repeat this process to get our other vector going from the origin to that oxygen atom. I won't repeat it, but the mathematical process is the same. You just replace the fractional coordinates for the appropriate one for oxygen, these three, to get to the second vector. So these are now two different vectors going from the origin, but to the bismuth, and the other one to the oxygen. And once you have these two vectors, we can actually get the vector in between these two atoms. So say we want the vector going from bismuth 1 to oxygen. So this vector you can get by subtracting these two other vectors. So say we start off from bismuth 1. If we go in the opposite direction, if we go in reverse, so negative RBI, then we go from bismuth 1 to the origin. And then if we add this vector for RO, then we would end up at this point. So by going minus RBI plus RO, you go from the bismuth to the oxygen. So then you can just subtract these two vectors from one another. So again, minus RBI plus RO is the same as RO minus RBI mathematically. So you can just, subtract those. So again, 4.27 minus 2.14 gives you 2.13. 0.79 minus 1.21 gives you minus 0.42. And 5.45 minus 5.93 gives you minus 0.48. So this is the vector going from bismuth to oxygen. And once you have that vector, you can work out the length of that vector just by doing some Pythagorean math. So to get the length of this vector in three-dimensional space, you take the square root of the square of each of these, 2.13 plus minus 0.42 and the square of minus 0.48. So if you work that out, then it becomes 2.22. So the distance between bismuth and oxygen in this case has been calculated to be 2.22. So this is also how a lot of crystallographic visualization software, how they measure distances. And this will come up in some of the exercises that you'll find in the course notes. So I hope the math repetition yesterday has allowed you to kind of follow what we've been doing right now with these points in the unit cell and also distances between atoms in the unit cell. Okay, now moving on to a very different topic. So the production of X-rays, starting off with the production of X-rays in an in-house laboratory X-ray diffractometer. So very often we will use what is called an X-ray tube. This is the kind of standard or most common way X-rays are generated at a university facility. I hope I have, okay. Normally in the classroom, I actually have an X-ray tube that I have at hand that I can show you, but I don't have one today, unfortunately, just a schematic. But we start off, let's say, let's describe this filament here, your cathode here. So here, current is passed through the filaments, and by applying a potential, we can pull off these electrons from the filaments. And these electrons are shot out from the cathode, and there's a chunk of metal, this targets that the electrons are bombarded towards. This is also the anode. So electrons come from the cathode and they're bombarded and hit the anode. Some metallic plates of some sort. So when you do this, or actually, I'm getting a bit ahead of myself. So the anode, typically, it's made out of something like copper or molybdenum. These are the most common sources of X-rays. And once you bombard these metals with electrons, X-rays are emitted. So there's two different types or two different categories of X-rays that are produced in this process. There's Bremsstrahlung, which gives you continuous X-rays, so it's a spectrum of X-rays. But you also get characteristic X-rays, and these characteristic X-rays are very dependent on the elements that this anode is made out of. Now, if you're lucky, you might have one of these rotating anodes. Now, so with the rotating anode, the anode is not stationary, but it's, as the name suggests, it's rotating. Now, why would you want to do that? Well, with a standard X-ray tube where the anode is stationary, you're constantly bombarding that anode with a lot of electrons. This generates a lot of heat. And of course, you don't want to melt your anode, otherwise you won't be left with an anode after a long time. So typically we have a cooling system. So there's water that comes in and out to remove the heat that is produced by bombarding that anode with electrons, excuse me. So cooling is a really big issue. But if you have a rotating anode, so say this is your cathode, your filament, so electrons are being emitted from the cathode and they hit the rotating anode here. But since the anode is rotating, you're no longer hitting the same spots all the time. You're changing the position of the spot that's being irradiated. So so this doesn't heat up the anode as much as, say, like a stationary X-ray tube. So with a rotating anode source, you can actually you have less of a heating problem, which means you can bombard more electrons on your anode, essentially creating a more intense X-ray beam. So this is just a way to deal with the cooling issue. So starting off with characteristic X-rays, so one of the two different categories of X-rays that are produced. So with characteristic X-rays, like I said, this really depends on the anode material, what element that chunk of metal is made out of. So with characteristic X-rays, we have that electron beam hitting the anode. So these, you can imagine, these are atoms within that anode material, the metal that is producing the X-rays. So from this electron beam, we have electrons coming in and they hit the atoms. They hit electrons of the atom. So this inbound electron, it might hit some inner shell, so low energy electrons in that atom in the anode, and it will cause those electrons, those low energy electrons, to be emitted from the atom. So both the electron that comes in and goes out, but also it ejects electrons that were originally in that anode material. So when that happens, you have vacancies, so missing electrons in your low energy shells. So when that happens, a high energy electron that is in that atom will relax and fill that position of the missing electron. And this causes this difference in energy from a high energy to a low energy orbital, releases energy from the atom in the form of an X-ray photon. So these X-rays have very specific energies, very specific wavelengths, because in atoms, these energy levels are very well defined. So you get very specific wavelengths of X-rays coming out, which are dependent on the anode material, what element it's made out of. Oh, okay, and yeah, this is just kind of the same thing, just showing you an electron coming in, going out, creating a vacancy in an inner shell orbital. So these inner shell orbitals we call the K shell, and kind of the next orbital we call like the L shell, and the M shell is even higher in energy. Okay, and yeah, so like I said, once we have a vacancy in a lower energy orbital, an electron from a higher energy orbital will relax and take its space, and this releases X-rays. This particular kind of X-ray or difference in energy that I plotted, this is known as K alpha radiation. So when you have an electron from an L orbital relaxing and filling a K orbital, a missing K orbital electron. This we call K alpha radiation. K beta radiation will come from even higher orbital energy orbitals. So if of an electron coming from an M orbital and relaxing and filling that missing K electron, this we call K beta radiation. So with K beta radiation, the energy difference is larger compared to the K alpha radiation. So if you see this kind of on an energy, this is just a very simplified energy level diagram. So again, say you have your electron vacancy in the K shell, this say like the 1s orbital of a metal. You can have electrons from higher energy orbitals relaxing, whether from the L orbitals or the M orbitals. And there's selection rules. So say higher energy electrons in s orbitals, say from the 2s or 3s orbitals, these are forbidden from going into the 1s orbital. You need a difference in quantum number of 1. So typically you have p electrons that are relaxing and kind of filling that vacancy in the 1s orbital. So that's why you have a limited number of kind of characteristic X-rays. So like I said, K alpha comes from electrons in the L orbitals, K beta comes from electrons relaxing from the M orbitals. And like you saw in the previous diagram, so the energy difference is larger if it's an M orbital electron that's relaxing, which means that K beta radiation has higher energy because that energy difference is different. So the X-rays have high energy, and higher energy when it comes to waves means a shorter wavelength. So K beta has a shorter wavelength than K alpha. So now with Bremsstrahlung, so this is like a continuum of electrons that is emitted. So this happens when, so we have electrons being emitted from the filament and hitting the anode material. But some of those electrons will decelerate and kind of slow down. So Brems in German means like breaks, to slow down. So this Strahlung is radiation. So it's breaking radiation. So radiation from electrons decelerating. So we get this continuous background of X-rays also emitted by the X-ray source. So actually the spectrum has both the Bremsstrahlung, this continuous background, but also peaks from the characteristic X-rays. So this is what we see, the combination of Bremsstrahlung and characteristic X-rays coming from our X-ray source. So say you have a copper anode, a copper target. This might be the spectrum that you see with a very specific value for K alpha and K beta for copper. But say if you change the X-ray anode and change it to molybdenum, and the spectrum looks different. Those characteristic X-rays they have very different wavelengths compared to, say, copper radiation. So in a lab source, to change the wavelength of the X-rays, at least of the characteristic X-rays, what you need to do is change the anode material. And sorry, we've already talked a little bit about the K alpha and K beta. Okay, and probably the most two common sources of X-rays, like I said, are copper and molybdenum. Copper K alpha 1 radiation has a wavelength of 1.54 angstrom. Molybdenum K alpha radiation has a wavelength of 0.71 angstrom. So you'll come across these two wavelengths very often. And it is good to recognize these two. All right, but there's also, of course, other ways X-rays can be generated, or other facilities one can go to use X-rays. So these are synchrotron radiation facilities. These are typically national facilities or international facilities. And basically it's largely based on Bremsstrahlung. And we have a whole lecture later on in the course just about synchrotron radiation and also neutron facilities as well. So today I won't go into much details, But I will say that at a synchrotron radiation facility, you have much higher intensities of X-rays, which means that you can do faster experiments, or you can do experiments where the in-house source is insufficient in intensity. Maybe the scattered X-ray beam is just too weak, that is hardly detectable. If you take the same crystal to a synchrotron source, maybe you can detect enough X-rays for a good diffraction experiment. Also with the synchrotron radiation facility, you can tune the wavelength, since it's not dependent on these like characteristic X-rays that you get from an X-ray tube or a rotating anode. So you can pick a wavelength and work with that. It depends a bit also on the beam line. Some beam lines have a fixed wavelength that they can operate at, or some beam lines you can change the wavelength to what you want it to be. You can also have monochromatic beams, or white, and you can also have white beams. So with a white beam, you have a polychromatic beam. That means that your X-ray beam, it's not monochromatic, that it has a spectrum of different wavelengths being shot out at the same time. And also, because these facilities are usually well funded, they tend to have state-of-the-art detectors, and also a variety of different sample environments, you know, high pressures, gas environments, high temperature, low temperatures, things like that. Now, there are disadvantages to synchrotron facilities. First of all, usually they're quite popular. That means there's a lot more people who want to use it than there is time available. So typically one needs to write a proposal, and if the proposal is accepted, then maybe a few months down the line, you might be able to go to the synchrotron and collect data. But usually that's not guaranteed. So usually it is a process that can take quite a few months just to get beam time. Also, with a much higher X-ray beam, much higher intensity of the X-ray beam, you can also damage crystals a lot faster. So beam damage becomes much more problematic compared to, say, an in-house source. So yeah, if you go to a synchrotron facility, be careful if your crystal is being destroyed by the X-ray beam. All right, so I have, I think 12 minutes before noon, so I will respect the time. We will resume at 1 o'clock to introduce the projects, but also if I'm not sure if I'll finish exactly on time. So if I go a little bit over time, I'll actually resume after lunch. Okay, so I think this is one of the final topics we're going to talk about today, the absorption of X-rays. So this is quite important because your crystals will not only scatter the X-rays, but they will also absorb the X-rays. And this is going to be dependent on the shape and size of the crystal that you have. So absorption of X-rays can be modeled with the Beer-Lambert or Lambert-Beer equation. So say you have X-rays coming in with a fixed intensity. Your incident beam has a known intensity, let's say. But like I said, the crystal is going to absorb some of that X-ray, and not all of it will be transmitted through the crystal. So perhaps you would expect that the X-ray beam coming out of the crystal has a lower intensity compared to the incident X-ray beam. And this is going to depend on the thickness of the crystal, as well as what elements you have in there, and also the density of the crystal. So basically, the more electron density that you have in your crystal, and the more X-rays will be absorbed. So say, so we can describe the absorbance, or on the contrary, the transmission of X-rays with this equation. So the transmission is equal to e to the power minus nu r. So what do I mean by that? So r is actually just the thickness of the crystal that the X-rays have to penetrate through. So that would be, if the X-rays are coming in, here it hits the crystal. So this is kind of the thickness of the crystal that the X-ray, the direct X-ray beam passes through. So that's the thickness of the crystal in that direction. And nu is the linear absorption coefficient. So this is unique to every crystal structure. So this parameter It has one value for the whole crystal, but it will depend on, like I said, the density of the crystal and what elements that you have there. If you have heavier elements, say like lead, that's going to absorb X-rays much more efficiently than a lighter element, say like hydrogen. So if you have a lot of heavy elements, then your linear absorption coefficient is going to be much higher. And what we aim for in an X-ray experiment is to have roughly about like 10% for the transmittance is quite ideal. If the transmittance is much lower, then your crystal is acting like a beam stop, essentially. If the transmittance is too high, then the X-rays are just kind of like going through the sample and not being scattered very well. So 10% transmittance it's quite good. So let's go through one example together. So let's say for one particular crystal structure, the linear absorption coefficient is 14. This is usually calculated by software. So if you know the unit cell parameters and if you know the crystal structure, then this is something that is calculated and something that you automatically get by most crystallographic software. But let's say the length of the crystal in this direction is 0.17 millimeters. You can just throw these values into the equation, and you can work out that the transmittance is, in this case, 0.09. So 9%. It's quite close to 10%. So that's quite a good transmittance. So this combination of this linear absorption coefficient with that thickness of the crystal is quite ideal. Now let's say you were to rotate the crystal so that rather than having the shortest length of the crystal being the path that the X-rays go through, now we have the longest length of the crystal in the X-ray beam. Now the linear absorption coefficient, like I said, this is dependent on the crystal structure, so that doesn't change just by changing the orientation of the crystal. But the path length that the X-rays take through the crystal has increased quite a bit. So say now after rotating the crystal, now the length of the crystal in the beam is 0.24 millimeters. So then we can put this in the same equation again. But now for R, we have 0.24 instead. Now this gives us a transmittance of 0.03, so about 3%. So this is considerably less, but at least you still have some X-rays going through. So you get the minimum transmittance through the longest length of the crystal, R max, and you get the maximum transmittance through the shortest length of the crystal. So I think that makes, it's quite obvious, this relationship. Now, you might see, like, if you know the dimensions of the crystal, you should be able to predict what the maximum and minimum transmittance are. But in practice, this isn't always the case because the crystal has to be on some sort of mount, some sort of support. It can't just be suspended in air, right? So you need to mount your crystal on something. Now, by mounting a crystal, it might kind of block certain directions of the crystal being probed by the X-ray beam. So for example, you can't rotate this crystal so that the longest length of the crystal is in the X-ray beam, because in this case, then the mount would block the X-ray beam. So you might not be able to have the longest length of the crystal oriented in the X-ray beam. So this might, if you know the values of the dimensions of the crystal, then your calculated transmittance, the minimum and maximum transmittance, might not be what you experimentally observe because of limitations of how you can rotate the crystal. All right, so in order to describe the shape of the crystal, quite often we'll use a video camera that's attached to the X-ray diffractometer. So we can rotate the crystal, and then we can outline a map, kind of like the three-dimensional kind of outline of the crystal. So by that, we can work out, the dimensions of the crystal and also the path that the X-rays go through in the crystal And we can do that not only for the direct beam that just goes through the sample, but we can also calculate the path length of every diffracted beam in the crystal as well. And we actually need to take this into account because, like I said, the thickness of the crystal will like dampen the intensity of the X-ray beam that comes out of the crystal. So not only does the structure influence the intensity of the scattered X-ray beam, but also the size and shape of the crystal as well. So we actually need to apply a correction, an absorption correction, for every reflection in the diffraction pattern. So yeah, this fortunately is quite automatically calculated by the software. Now, again, related to the absorption of X-rays. So every element absorbs X-rays differently. So we were talking about X-ray emission, but now I'm talking about X-ray absorption. So with every element, this is kind of the absorption spectrum. So say for copper, if you were to irradiate a chunk of copper with an X-ray beam and you change the energy of the X-ray, if you change the wavelength of the X-rays, you'll see, yeah, that it's not continuous, that you'll see at some energy a sharp rise in the absorption of the X-rays by that element. So this sharp rise is known as the absorption edge. So this occurs, so say we have a chunk of copper metal, and you irradiate with X-rays now, not electrons like we were talking about with X-ray emission, but now if we irradiate copper with X-rays. So X-rays are ionizing radiation. That means it can knock out electrons from atoms. So say we have an electron in the 1s orbital, the K shell in copper, and you irradiate it with X-rays. So once you reach a certain energy threshold, once you reach that absorption edge, you have enough energy to knock that electron out of the atom into the continuum. So this absorption edge is dependent on the energy of the 1s orbital, this K shell electron orbital. So as soon as you have enough energy from the X-rays to knock it out, then you have that absorption edge. And if you go higher in energy, actually the absorption is decreased. So you have maximum absorption right when the X-ray beam has a similar energy as the relative energy of that 1s orbital there. Okay, so why is this important? Well, say you have a copper X-ray source, a copper anode that is generating X-rays. So based on the characteristic X-rays, so the K alpha 1 radiation of copper, like I said before, is 1.54 angstrom. So that's the wavelength of the X-rays that is generated by a copper source. Now, if you have a crystal sample, if that sample contains certain elements like cobalt, iron, and manganese, now these elements are excellent at absorbing specifically copper K alpha radiation. So this is the absorption edge of cobalt, iron, and manganese. And you see these are just above the wavelength of copper K alpha radiation. So if you have any if you have any cobalt, iron, or manganese in the sample, it's going to absorb a significant part of the X-ray beam, which means you're not going to have much X-ray coming out of the sample. That's these samples are really good at being beam stops for specifically copper K alpha radiation. So you won't be able to collect very good diffraction data if you're using a copper X-ray source and if your sample contains manganese, iron, or cobalt. So what can you do? Well, if you really want to study samples with manganese, iron, or cobalt, then if you can, it's best to change the copper source of the X-rays. So this is where like molybdenum radiation comes handy. So molybdenum is off this chart, but molybdenum has its K alpha 1 radiation at 0.71 angstrom, which would not be absorbed heavily by manganese, iron, or cobalt. So keep that in mind, especially if you are working with manganese iron or cobalt samples. If possible, try to avoid an X-ray source that's based on a copper anode. And again, this is the advantage of synchrotron radiation. If you do have samples with these elements, you can tune the wavelength of the X-ray beam. So it's not a wavelength that is particularly heavily absorbed by your sample. Okay, I know it's 12:01. I'll be done in just a few moments. So here is the absorption spectra of nickel. Here it's plotted against wavelength rather than energy. Now, if you look at the emission spectrum of copper, so if you're generating X-rays with a copper anode, you have both K alpha and K beta radiation. Now, if you compare that to the nickel X-ray absorption spectrum, you see that nickel is very good at absorbing X-rays up to about like 1.4, what is that, like 1.45 angstrom. But it's very poor at absorbing X-rays at higher wavelengths. So actually, nickel is very good at absorbing K beta radiation, but not copper K alpha radiation. So if you put a sheet of nickel in an X-ray beam that's generated with a copper source, it will absorb most of that K beta radiation. So without the filter, you have a lot of, without that nickel filter, you'll have a lot of K beta radiation, but as soon as you put in the nickel filter, it will absorb most of that K beta radiation and let most of the K alpha X-rays through. So this way you can try to make your X-ray beam more monochromatic, so that you remove high intensity X-rays that don't belong to this K alpha peak. Okay, it is lunchtime. There was one more point that I wanted to talk about, but I think we'll resume after lunch. So yeah, after lunch, we'll just go through these last few slides on the density of a crystal, and I'll also introduce the first project. So I'll stop the recording.